Good evening, ladies and gentlemen. Welcome to today's seminar, Sustainable Biological Wastewater Management, Paradigm Shift in Recent Years. We are delighted to have Dr. Liu Tao to deliver today's seminar. Dr. Liu is currently the Assistant Professor in the Department of Civil and Environmental Engineering, the Hong Kong Polytechnic University. Dr. Liu published over 60 papers in the past 5 years in peer-reviewed journals, including Nature Water, Nature Sustainability, Energy and Environmental Science, the ISME Journal, Environmental Science and Technology, and Water Research, situated at the juncture of environmental microbiology and environmental engineering. Dr. Liu's research focuses on explorations of novel microorganisms and applying these newly discovered microbial reactions in tangible applications. These applications manifest notably in the treatment of wastewater and waste sludge, as well as the upgrading of biogas and syngas, thus ultimately contributing to the advancement of sustainable environmental practice. May I now invite Dr. Liu to deliver the seminars today. Dr. Liu, please.
Thank you, Liu, for the very kind introduction. So firstly, before I jump into my presentation, I would like to quickly go through a short introduction for our department, the Department of Civil and Environmental Engineering at PolyU. So as you have already seen in the past a few slides, we have quite a lot of significant achievements in the field of civil engineering and environmental engineering. And we have very fascinating and world-leading facilities, including laboratories, workshops, and one research center at Shenzhen. If you want to connect with us using any kind of channels, you can take a photo of these slides. Okay, so thank you again for the invitation to let me give a short presentation on the topic of biological wastewater treatment. So actually, I would like to give a very quick introduction for myself. I got my bachelor degree almost 10 years ago in 2015 from Tsinghua University. And then I went to Australia to pursue my PhD degree in water management, particularly in urban water management. I graduated and I got my PhD degree at the beginning of 2020, just before the pandemic. And then I decided to stay in Australia to start my postdoc position and then research fellow position at the University of Queensland. From this year, the beginning of this year, I moved back to Hong Kong. I joined Hong Kong Polytechnic University, CE, as an assistant professor working on the urban wastewater management topic. Okay, so firstly, I would like to give a very quick review about the biological wastewater treatment, the history. So indeed, before the 19th centuries or before the 18th centuries, the wastewater treatment is not really a focus or not really a concern for the society by that time. So as you can see from these left figures, the wastewater we generated by that time mostly were directly discharged into water, into rivers or into the oceans. So this, because of this untreated wastewater discharging into the nature ecosystems, it caused a lot of public health issues. For example, there were a few very serious pandemics happening in Europe during the 18th centuries because of the bacteria or the viruses in the wastewater, untreated wastewater. After realizing the importance of wastewater treatment, people started to develop biological wastewater treatment plants across the entire world. So in the 19th to the 20th centuries, the process named the activated sludge system has been developed across the world as the most famous and even nowadays, I think it's the most popular biological wastewater treatment process. So now, when we move into the 21st century, the question becomes, where are we going to? The wastewater treatment process, where it should go into. So this is really the question for all the water engineers and for all the water scientists. So if we look at if we look at the most significant changes happening in our daily life in recent years, you will be able to find most of these changes are really based on some very significant fundamental findings. For example, the self-driving cars or the wireless charging technologies. This kind of new technologies, they are really developed based on some new fundamental findings in the relevant research field. So the same case for our wastewater treatment. So for the wastewater treatment, because I think most of you know, we utilize or we rely on some microbial process, we rely on some biological process for removing the contaminants from wastewater. So that's why the fundamental discovery of some new microbial process or of some new biological process is really the becoming the foundation for the development of new biotechnologies for wastewater treatment. So this is really the logic between the new technology development and the new fundamental knowledge we obtained from our research. So in one of our recent publication, we kind of summarize all the significant fundamental findings in the past 50 years and all the significant technologies we developed in the wastewater treatment in the past 50 years. So this is a very big figures, but you can see from part of this figure, the fundamental discoveries, which is labeled as the black line, and so let me put my laser pointer. Okay, so as you can see from this figure, the fundamental knowledge, fundamental findings under the technology development are labeled using different colors, but they are one very general conclusion from this figure is the development of new technologies and the discovery of some new fundamental knowledge are always connected with each other. So basically speaking, the fundamental discovery supports the development of new technology, and in turn, the development of new technology also supports the discovery of more new fundamental findings. So that's really the beginning of my presentation. Now I'll take one of the examples to give you more detailed explanation. So in wastewater treatment for the biological nitrogen removal process, because the nitrogen removal is one of the most important topic for the wastewater treatment. So in previous wastewater, in the traditional wastewater treatment process, the nitrogen removal is achieved by two processes named nitrification and denitrification. The nitrification process converts the ammonium nitrogen in the wastewater into nitrite and then into nitrate. And the denitrification converts nitrate back to nitrite and then to nitrogen gas. Therefore, by using nitrification and the denitrification, the ammonium contaminants in the wastewater will be eventually removed as the dinitrogen gas from the wastewater. So this is the traditional wastewater treatment process. However, one of the very important issue for the nitrification and the denitrification process is for the nitrification process, as you can see here, it will consume a lot of oxygen, so which means it will require a lot of energy input. While for the denitrification, it will utilize a lot of organics, which means we need to add a lot of chemicals, organic chemicals into the wastewater in order to remove the nitrogen eventually as the nitrogen gas. So that's really the issue for the traditional nitrification and the denitrification process. We need energy and we also need organic chemicals. So in order to address this question, in the past 20 years, people started to develop a new technology based on the discovery of a new microbial process named Anamox process. Anamox process. The Anamox process is a very unique process driven by a bacteria. In this process, as you can see here on this equation, the ammonium and nitrites can be removed by this bacteria as nitrogen gas eventually. So it means these bacteria that do not need organic as their carbon source. They can remove the nitrogen from the wastewater autotrophically. That's really the beauty for this new microbial discovery. So based on this fundamental discovery, researchers at the water industries started to develop technologies utilizing Anamox bacteria to remove nitrogen from the wastewater. Here, we proposed a concept to remove nitrogen in the wastewater utilizing Anamox. The name for this process is partial nitration plus Anamox, or shortened as a PNA process. In this process, the ammonium in the wastewater will be oxidized into nitrite. And this nitrite, together with the ammonium, will be removed by the Anamox bacteria as the nitrogen gas. As you can see, if you compare this partial nitration Anamox process with the traditional nitrification denitrification process, you will see we save the oxygen consumption in the second step of nitrification, and also we save all the organic consumption used in the traditional denitrification process. So we save oxygen consumption, we save energy consumption, and we save organic chemical consumption. So that's really the advantages of this partial nitration Anamox process. Another advantage is this process generates much less sludge compared to the nitrification denitrification. So because the sludge generated in the wastewater treatment plant will require additional treatment or management. So that's why by utilizing partial nitration Anamox, we can achieve a lot of different advantages. Okay, that's really the beginning of my own research story. The research center where I got my PhD degree in Australia has been working on the Anamox application for more than 10 years already. And initially my PhD project was funded by three water industries in Australia: Melbourne Water, South Australia Water, and the Urban Utility of Queensland. So in this project, we try to demonstrate the Anamox technology at the pilot scale. As you can see from this figure on the right-hand side, in one of the wastewater treatment plants located in Queensland, we established this pilot scale wastewater treatment system, including including all these different units shown on the left-hand side. So that's really the beginning of my own research. And also because of this experience working in the water industry, I have learned a lot from the water and wastewater engineering. And because of this experience, I really have the opportunity to learn what the water industry what's the real requirement and what's the real needs from the wastewater industry. However, one of the facts I want to share with you is this Anamox process nowadays has been applied for more than 200 wastewater treatment plants already, full-scale applications, more than 200 applications. But the fact is, all these full-scale Anamox applications are utilized to treat or to remove nitrogen from some side stream wastewater. So what is side stream wastewater? Side stream wastewater means some very special wastewater, such as the industry wastewater or some anaerobic digestion liquor or landfill leachate, this kind of wastewater. So a unique feature for the session wastewater is they usually have very high concentration of nitrogen pollutant in the wastewater. However, for the very normal or the most common domestic wastewater, the sewage, the current application of NMOX is very, very limited. I have to say, at the current stage, across the world, there may be only a few successful full-scale NMOX applications for treating domestic sewage. So why the NMOX technology cannot be applied for the domestic sewage treatment? There are mainly two major challenges. The first challenge is about the NOB suppression. So what is NOB suppression? Again, come back to these figures as you can see here. In order to utilize NMOX, partial nitritation NMOX, we need to suppress the second step of nitrification, which is the conversion of nitrite to nitrate. We need to stop this process. We need to suppress this process using some strategies. We need to kill this bacteria, or we need to inhibit this bacteria. However, the fact is suppressing NOB, the bacteria contributing this second step, suppressing this NOB is extremely challenging in the mainstream sewage. It's extremely challenging. Two of my students, actually, Yan is my first PhD student, and Sue is the first PhD student I co-supervised. These two students, they utilize laboratory study, mathematical modeling to prove the reasons why the NOB suppression in the mainstream condition is extremely difficult compared to the side-stream wastewater, which I will not go into too much details, but the conclusion here is NOB suppression is very difficult in the mainstream sewage. That's one of the challenges for applying NMOX in the mainstream sewage treatment. The second challenge about the mainstream NMOX is the limited nitrogen removal efficiency. Let's come back to this NMOX equation. So one thing I didn't mention to you in previous slides is while removing ammonium and nitrite as nitrogen gas, the NMOX bacteria will also convert some of the nitrogen into nitrate. The nitrate will be, it means while remove majority of the nitrogen in the wastewater as nitrogen gas, it will leave about 10% of the nitrogen as nitrate in the final effluent. So that's why the total nitrogen removal efficiency for the NMOX process is around, slightly below 90%, which could be even lower in the practice. So that's the second challenge for the NMOX application in the sewage treatment, in the domestic wastewater treatment. So that's why our research group wants to develop some strategies to overcome these two challenges in order to make the NMOX applications applicable to the sewage, to the domestic wastewater treatment. So in order to overcome the first challenge, we got some inspirations from the side-stream application. Remember, I just mentioned that NMOX has been applied widely for the side-stream wastewater already, more than 200 full-scale applications. Why the NMOX can be applied in the side-stream wastewater? One of the very important facts is in the side-stream wastewater, the wastewater has very high concentration of nitrogen. Because of the high concentration of nitrogen, even at pH 6.5, relatively neutral pH, it will naturally form a chemical named free nitrous acid, shortened as FNA. FNA concentration can be automatically reach 1 to 3 ppm level in the side-stream high-strength wastewater, because there is an equation to calculate the FNA concentration as shown on the above. The FNA concentration is related to the pH and related to the nitrite concentration. So in the side stream wastewater, because of the high nitrite concentration, the FNA level can easily reach 1 to 3 ppm level. And this FNA is a toxic chemical actually. FNA, because of the toxicity of FNA, it can very easily inhibit or suppress NOB, this bacteria. Therefore, the second step of the nitrification can be very easily suppressed or inhibited in the system wastewater. Therefore, NMOX process can be easily applied in the system wastewater. That's the reason behind the 200 full-scale applications of NMOX in the system wastewater. It's very easy to apply NMOX in the system. However, if we come back to the mainstream domestic sewage, the case will become very different because the domestic wastewater, domestic sewage, the total nitrogen is only around the 50 ppm, 50 milligram per liter. Therefore, the highest nitrite concentration in the domestic sewage is the 50 ppm. Based on this equation, at pH 6.5, nitrite concentration around 50 ppm, the FNA concentration will be only at the ppb level, almost 1,000 times lower than that achieved in the system wastewater. This kind of low FNA level cannot suppress NOB easily. So that's why in the mainstream domestic sewage, the NOB suppression is very difficult. Therefore, the NMOX application is also very difficult to be achieved. So this is the reason why the side-stream NMOX can be achieved easily, while the mainstream NMOX cannot be achieved easily. So because of these findings, because of these reasons, we ask ourselves, can we also achieve FNA at the ppm level, even in the mainstream domestic sewage? Can we achieve that? Then we come back to this FNA calculation, this FNA calculation equations. So as I mentioned, the FNA concentration is not only related to nitrite, it's also related to the pH. So it means even for the mainstream wastewater, if we can operate the mainstream bioreactor at the pH 4.5 to pH 5.5, if we can achieve this slightly acidic pH in the mainstream wastewater, the FNA concentration will dramatically increase to the ppm level. So this is really the inspiration we got from the successful experience in the side-stream NMOX application. So if we want to apply NMOX in the mainstream, one of the strategy we develop is to utilize acidic mainstream domestic wastewater treatment. However, the fact is all of the mainstream biological wastewater treatment or all of the current biological wastewater treatment plant are usually operated in the neutral pH. For example, pH 7, pH 6. So none of these treatment plants has been utilizing acidic pH for the biological reaction. Why they don't utilize acidic pH for the wastewater treatment? The reason is most of the microorganisms, they can only survive at a neutral pH, while at acidic pH, they will be killed or they will be inhibited. Majority of the microorganisms or the biological reactions we currently use will be suppressed or killed. So therefore, we wonder, can we find some new microbial process or biological process which can tolerate, which can survive at the acidic pH? For example, pH 4.45 or pH 5.5. That's really the inspiration or the starting point for our research. So we want to find some acid tolerant bacteria which can survive at acidic pH in order to achieve the goal I just mentioned. So therefore, we look into the literature, we found that, okay, the acid-tolerant AOB, the acid-tolerant bacteria, exist in many nature ecosystems. There are many different publications have already found the acid-tolerant bacteria from the acidic soil system. And therefore, based on these discovery from nature ecosystem, the research group led by my previous supervisor, Professor Zhu Guoyuan at UQ, we try to enrich such acid-tolerant bacteria in our laboratory bioreactors. The fact is we were successful. So we successfully enriched the acid-tolerant bacteria in our laboratory reactor. As you can see here, the bioreactor, the pH of the bioreactor gradually decreased from around 7, the neutral pH, to pH 4.5 or to 5.5, this level, acidic pH. And during this process, we found the traditional bacteria that currently utilized in the wastewater treatment plant disappeared. For example, the Nitrosomonas, Nitrospira, and the Nitrobacter, they disappeared after 200 days. And gradually, a new bacteria named Nitrosol globus appeared in our bioreactors and become the dominant bacteria in the reactor. So it means at this acidic pH, the new bacteria were enriched in this in our laboratory reactors. So by utilizing this newly enriched bacteria, the acid-tolerant bacteria, our previous hypothesis become true. So we can utilize this bacteria to operate the bioreactor at 4.5 to 5.5. So if that's the case, even at mainstream domestic sewage, we can achieve ppm level FNA, and because of this high FNA, we can suppress NOB, and then we can apply Animox technologies. So that's really the reasons and the hypothesis behind our research story. And the first PhD student, the second PhD student, Liu, his PhD focused on the development of technologies utilizing this acid-tolerant bacteria, acid-tolerant AOB in wastewater treatment. So in his research, we developed a membrane system. We developed a membrane biofilm system to cultivate this acid-tolerant AOB in our laboratory. As you can see from these results, in this almost 1-year operation, the pH of this reactor also gradually decreased from neutral pH to this acidic pH around pH 5. And because of this low pH, the FNA concentration we achieved is around 1 ppm. And because of this 1 ppm FNA, we successfully suppressed the NOB, the second step of nitrification, and eventually achieved the Animox technology, which I will not go into further details. But one of the very interesting phenomena I want to highlight here is the rate, the nitrification, or the biological rate, the nitrogen removal rate we achieved in this study is 1 order of magnitude higher than the rate currently utilized in the wastewater treatment plant. For example, in the current wastewater treatment plant, the nitrogen removal rate is usually about 0.2, 0.3 kilogram nitrogen per cube per day. And in this research, the total nitrogen removal rate we achieved is around 2.3 kilogram nitrogen per cube per day. So that's really one of the very significant finding we found from this research. Again, similar phenomena as I just showed you, the traditional bacteria disappeared along this process, while the new bacteria, acid-tolerant Nitrosol globus, gradually enriched in our bioreactor, which has been confirmed using different methodologies. So that's our application of this new bacteria in wastewater treatment. Actually, in addition to wastewater treatment, we also apply these bacteria for some sludge treatment, for the sludge treatment, because for the wastewater, we generate a lot of sludge, the primary sludge and the secondary sludge. So one of the very traditional approach to manage the sludge is to add some acid to regulate the sludge pH. For example, if we add some acid to acidify the sludge to pH 4 to pH 5, we can achieve the sludge reduction and the stabilization purpose. And if we further decrease the sludge to pH 2, we can we can remove some heavy metals from the sludge. And in order to landfill this sludge, eventually we also need to add some base to raise up the pH again. So this is really a traditional way to manage the sludge in current treatment plant. So now we propose a new strategy to manage the sludge. So the principle or the concept is we can utilize the bacteria nitrogen conversion to regulate the sludge pH. Why we can do that? It is because, as we can see here, I have listed two equations here. So for the nitrification process, when the ammonium oxidizes to nitrite, it will also generate some protons. While for the denitrification process, while the nitrite reduced to nitrogen gas, it will generate some alkalinity. So if we can utilize the protons generated in the nitrification and the alkalinity generated from the denitrification, we can easily regulate the sludge pH from neutral pH to the acidic pH and then back to the neutral pH again. So this is the principle or the hypothesis for our technologies. So that's why we proposed some technology to achieve this goal. For the sludge, we mix the sludge, for example, the primary sludge or the secondary sludge or even the AD sludge, together with the acid-tolerant bacteria we enriched in the lab. We mix these two cultures together and we put some aerations. Because of this first equation, because of the protons generated, the sludge pH will gradually drop to 4 to 5. If we only target the sludge reduction and the sludge stabilization, pH 4 to 5 is already enough. If we also want to target the heavy metals removal from the sludge, we can further push the pH down to 2 or even lower to remove the heavy metal from the sludge. While we achieve these goals, we can utilize the denitrification process to raise up the pH from 2 to 7 again. So as you can see, compare this traditional process, we don't need to add any acid or alkaline into the sludge anymore. We only rely on the nitrogen conversions in the sludge to achieve the sludge management different goals. And in addition to these traditional goals, as you can imagine, we also remove nitrogen. We also remove nitrogen in the sludge. That's the additional benefits for our technology. And in the meantime, because of the low pH, high pH variation, some of the emerging contaminants, like, for example, antibiotics, we also found that we can remove some antibiotics during this sludge management. So here are the results for our technologies, which I will not go into too much details because I already described these results to you already. As you can see, the pH for the first step can decrease to 2 from the neutral pH to 2, while for the second step, we can further drive up this pH to neutral again. So this is some detailed results. Okay, one more thing I want to highlight here is because we can drive up the pH back to neutral, so indeed we can also recover the heavy metals from the sludge. So you can imagine the heavy metals will be firstly removed from the sludge because of the low pH. They will be leached from the sludge into the supernatant, and then because the pH, once the pH raised up to 7, these heavy metals will become precipitate. So we can recover these heavy metals again from the supernatant. So that's what we achieved in our laboratory. Now let's do a very quick summary for the first stage. Our applications. So for the wastewater treatment, so by utilizing these acid tolerant bacteria, we can achieve both the more sustainable wastewater treatment and also more sustainable sludge management. So we can utilize the acid tolerant AOB and the NMOX for the sludge treatment and for the wastewater treatment, and also we can utilize the acid tolerant bacteria for the sludge treatment, which I have already covered. And one of the very important fact is in order to utilize the acid tolerant bacteria in the wastewater, it will require the wastewater has very low alkalinity, for very low alkalinity. But the fact is, for the most of the domestic sewage, the alkalinity is quite sufficient. It means we can't utilize acid tolerant AOB directly to drive the pH of the wastewater down to, for example, pH 4 or pH 2. We can't achieve that. So we have to add some acid to achieve this goal. The interesting thing is in Hong Kong case, about 80% of the wastewater in Hong Kong will be currently treated by chemically enhanced primary treatment, which means we usually add some ferric chloride to enhance the primary treatment. In addition to enhance the primary treatment, another factor by using ferric chloride is ferric chloride is an acidic chemical. If we add some ferric chloride into the sewage, it will automatically decrease the sewage alkalinity. So it means this acid tolerant process is particularly suitable for Hong Kong wastewater treatment comparing to other regions. Because for other regions, we need to add some acid, but for Hong Kong, we already add some ferric chloride to decrease the sewage alkalinity, which means we don't need to add additional acid to achieve the low pH. So this is the summary for the benefits we can achieve by utilizing this acid tolerant process and NMOX. The second challenge, remember we have the second challenge. The second challenge is we have a relatively limited total nitrogen removal efficiency because of this nitrate accumulated in the NMOX effluent. So we want to address this question as well. So one of the very traditional approach to address this nitrate accumulated in the final effluent is we can easily add some organic chemicals into the final effluent to polish the NMOX effluent. This is the traditional way. So, but again, adding some chemicals into the wastewater will lead to additional cost. So that's why we look into this wastewater treatment plant. We wonder, can we utilize the methane generated from the anaerobic sludge digestion in the biogas? Can we utilize this methane to drive the denitrification process? Because methane is also one of the forms of organics. Can we utilize methane as organics to remove this, to polish this NMOX effluent? So that's the second part of our research. So we wonder, can we achieve that? So this is also based on a new discovery. This is this new discovery. We discovered some new microorganisms which can achieve this goal. They can utilize methane as organic carbon to remove nitrite or to remove nitrate. So this is the very unique function and very unique bacteria. We propose by utilizing these bacteria, new bacteria, we propose some new technologies, trying to combine these new bacteria together with the Anammox bacteria. By combining all these bacteria together, you can imagine the nitrate generated from this Anammox process can be reduced by the Endamo archaea and Endamo bacteria, eventually as the nitrogen gas. So it means by combining all of these three bacteria or archaea together, we can eventually achieve almost complete or 100% nitrogen removal from the wastewater. So that's really the hypothesis we have. So by utilizing these, based on this hypothesis, it means we can utilize the biogas generated from the anaerobic sludge digestion to drive the denitrification in the wastewater. However, one of the very critical issue for this new technology is methane is an insoluble gas, or biogas actually is quite insoluble in the wastewater. It has very low solubility in the wastewater, and also it is a flammable gas. It also has some risk to be if we want to use it in the wastewater treatment. That's why, in the fact, we want to figure out a new bioreactor design to solve this problem, to enhance the biogas solubility or enhance the methane solubility. Then we proposed this new bioreactor design named the membrane biofilm reactor. The unique feature is for this new bioreactor is we have a lot of hollow fiber. Just like our hair, we have a lot of hollow fibers installed in the reactor. So in the lumen of this hollow fiber, we deliver the methane, or we delivered the biogas, and the methane molecular, they can diffuse from the inner gas phase into the outer bulk liquid, which is the wastewater. They can diffuse into the wastewater and dissolve into the wastewater very, very efficiently. So indeed, when you operate the reactor, you cannot see any bubble, very different to the traditional bubbling aeration utilized in the wastewater treatment plant. You cannot see any bubble on the surface of this hollow fiber. It is really it is a pure diffusion process, which can significantly enhance the biogas or the methane transfer rate. So by utilizing this new design, we developed some technologies to remove nitrogen from the wastewater. As I just mentioned, we utilize this design to remove the nitrogen from different type of wastewater. For example, the side stream wastewater with very high concentration of nitrogen, or the low mainstream domestic sewage with very low nitrogen pollutants. So we apply this technology in many different scenarios in our laboratory. Here is one of the examples. As you can see here, the left one is to treat the high strength wastewater. The concentration of the nitrogen pollutant is around 1,000. The second one is the low strength wastewater, around 50 milligram per liter nitrogen pollutants. For both cases, eventually, after 1 year operation, we demonstrate this technology is very efficient in removing the nitrogen from wastewater. The rate achieved and the removal efficiency achieved is satisfactory, can meet a very stringent discharge standard already. So which is a very promising configuration. Actually, in our research group, in addition to laboratory demonstration, what we really want to do is trying to promote such technology, to facilitate the adoption of such technology by the water industry. That's why we we try to promote this technology, scale up this technology at pilot scale. So we demonstrate this world first pilot scale in Australia, still in the pilot plant in Queensland, based on the collaboration from from three water utilities in Australia and the Australian government. We demonstrated this technology successfully at a pilot scale, which showed very promising results. So the second application scenario for this new bacteria is, as you can see, it can consume, they can remove methane as well. Methane is a greenhouse gas. So that's why we wonder, can we utilize this new bacteria, this N-bacteria, to mitigate the greenhouse gas? Because we all know the greenhouse gas emission is a very serious concern for the current wastewater treatment. So in terms of methane, there are two sources in the urban wastewater treatment plant. One is from the sewer networks. Another one is from some anaerobic sewage treatment process. There are usually a lot of methane emissions from these two units. Therefore, we developed some technologies to remove the methane emissions from these different units. Because as you can see, we remove nitrogen, we remove methane together. So that's why we say this new technology is really a one stone for two birds technology. We can achieve two goals using one particular technologies. For these technologies, we also have different technical route. So one-stage route or two-stage route, which I will not go into too much details today. I will give you a quick update for our recent results. As you can see for these figures, the nitrogen removal efficiency, the last figure, the nitrogen removal efficiency we achieved is almost close to 80%. While the methane removal, the methane emission removal efficiency is very close to 100%. So it can achieve these two goals simultaneously. Similarly, in another one-stage configurations, the methane, this is the nitrogen removal efficiency, also around 100%, and the methane removal efficiency is also around 90 or 80%. So we can easily mitigate the methane emissions and also remove the nitrogen from the wastewater. So that's the technologies we're trying to demonstrate in our laboratory. In addition to the technology demonstration, we are also very interested in the fundamental knowledge inside the technologies. So we developed some very sophisticated technologies to review the microbial process in the technologies we developed. For example, we developed some technology to just like scraping just like cutting a cake or scrap peeling an apple. We can see the granulars or the biofilms in depth using our technologies. So that's really some very interesting fundamental study we're trying to develop or trying to investigate in our laboratory. Another very interesting thing I want to share with you is we are also trying to connect the wastewater treatment with the gas, with the waste gas treatment. So as we know, for example, for T Park in Hong Kong, for the sludge incineration, there will be a flue gas generated, right? The flue gas contains in some cases they contain CO, CO2, and in some cases they also contain hydrogen gas. We are trying to develop some strategy to utilizing these flue gas as a source to remove the many different contaminants from water and from the groundwater. We're trying to connect the gas treatment together with the wastewater treatment. Okay, so that's very quick summary for our research. So in summary, the biological fundamental knowledge leads to the development of new technologies. And in turn, the new technologies are also a platform for us to learn some new fundamental technologies. And all these new technologies are really leading the next generation of wastewater treatment. The last two slides I want to share with you what we are doing here at PolyU. In PolyU, we are developing a research group focusing on the next generation urban wastewater management. In general, we summarize all the research directions regarding the future wastewater treatment plant into 5 categories. The first target is about the greenhouse gas emissions. So we want to, everyone is talking about the carbon neutrality. So that's why we want to develop some technologies to mitigate. So firstly, we want to develop something to monitor the greenhouse gas emission. And then we also want to mitigate the greenhouse gas emission across the entire urban wastewater systems. The second goal we want to achieve is to intensify the treatment capacity. We want to without a significant expansion in space, we want to develop some efficient strategy to intensify the treatment capacity of current treatment plants. The third goal for us is to develop some strategy to reduce the cost for wastewater treatment. For example, the NMOX technology, which can save a lot of energy consumption. The fourth goal for us is to consider some emerging contaminants in the wastewater, because we all know wastewater and the sludge is really a significant sink for many, many different emerging contaminants, such as antibiotics, microplastic, etc. The last goal for us is to do the resource recovery from the wastewater. Nowadays, we consider wastewater more as a resource rather than a waste. We want to recover more resource from the wastewater. This is the concept we draw for Hong Kong. So for Hong Kong, the wastewater treatment is very unique compared to other regions and countries, because 80% of our sewage is currently treated by chemically enhanced primary treatment only, while only 20% of the sewage will undergo secondary treatment, like in Shatian sewage treatment plant. So this is really the very unique feature for the sewage treatment in Hong Kong. And because of this, we can see there are many, many opportunities existing in the current treatment process in Hong Kong. For example, we all know there are many, many greenhouse gas emissions in different units. For example, in sewer networks, in the secondary treatment, and even in the marine system where the wastewater eventually discharge into. So that's why we are really keen to develop some strategies to monitor, to quantify, and to mitigate the greenhouse gas emission across the entire urban wastewater treatment in Hong Kong. And one very interesting and also very critical point I want to highlight here is for most of other regions or countries, the greenhouse gas emitted from wastewater sector only accounts for 2 to 4% of the total emissions of the entire society. But for Hong Kong, the emissions from wastewater sector can account for almost half of the total emissions. The reason for this large number is for Hong Kong, we don't have other very intensive industry. For example, power plant or petrochemical industry, we don't have such intensive industry. So that's why in terms of the fraction, wastewater sector contribute a lot of greenhouse gas emissions in Hong Kong as a whole. So this number is based on our very recent data mining from the IPCC report. So in the future, we want to get a more accurate number by measuring the real greenhouse gas emissions in the real wastewater treatment plant in Hong Kong. So in order to achieve this goal, we proposed 3 different working packages to target the 2-stage carbon reduction goal and the carbon neutrality goal, which is proposed by the Hong Kong government. By 2030, we want to reduce the carbon emissions by half, and by the middle of this century, we want to eventually achieve the carbon neutralities. So that's why we propose the different strategies for the water sectors. How can we achieve the 2030 carbon reduction goal, and how can we achieve the 2050 carbon neutrality goal, which I will not release too much details today. I hope in the future I have more opportunities to share more interesting research outcomes with everyone. So lastly, I would like to acknowledge all the support and particularly the funding support from my collaborating industries and also the government. Thank you all for listening. I'm happy to take any questions.
Thank you. Thank you, Dr. Liu, for your presentations. Now we come to the Q&A sessions. So we have got a couple of questions. Okay, the first question is, how can you remove the anomalous bacteria from the wastewater?
Okay, anomalous bacteria, we want to keep them in the wastewater. So that's why. So firstly, anomalous bacteria are not pathogenic or are not harmful for public health. So theoretically speaking, we don't need to remove them. And the second point is we want to keep them. So because we rely on them to remove nitrogen. So that's why we have some strategies to keep them inside the wastewater treatment tank. So they will not go outside go along with the effluent. They will be kept in the bioreactors.
Okay. So we have another questions on is any treatment cost reductions by using the innovative technologies?
You mean the number? Okay. So for the anomalous technology, theoretically speaking, it can save about 60% of total energy consumption, because we know for the wastewater treatment plant, the majority of the energy consumption is used for aeration. And using anomalous process can save a lot of aeration. So that's why we can save a lot of energy consumption. So around 60%, that's the theoretical number. In practice, it can be lower, maybe 40% or 50%, but still a very large number.
So by reducing the energy consumptions, we can also reduce the treatment cost, right?
Yes, definitely.
Okay. So we have another questions. With the low pH conditions affects the removal of other chemicals in the secondary treatment, like phosphorus?
Yeah. Okay. For the phosphorus, it's not possible to be removed, and actually, phosphorus removal rely on. In Hong Kong, we can use CEPT for removing phosphorus because of the chemical reaction between ferric and the phosphorus. And if you want to use biological reaction to remove phosphorus, that's a different story. So it's not based on the acidic process. But for other contaminants, for example, some emerging contaminants like antibiotics, pharmaceuticals, these kind of chemicals can be also removed in the acidic pH at certain levels. It can be also removed. That's the additional benefits by using acidic treatment.
So another question from Matthew. Is it possible that when the traditional nitrate denitrification system has high FNA levels, the animal's bacteria becomes dominant and convert the nitrate to nitrogen gas in the aerobic tank?
This is a good question. It's hard to say. It's hard to give you a very clear answer at current stage because, as I mentioned, initially people thought we can rely on the neutral pH to achieve this goal, but many attempts failed. So that's why we changed our mind. We shifted our technology to this acidic pH. So nowadays our perception is using acidic pH can be easier to achieve the partial nitritation NMOX process compared at neutral pH. Although I also want to mention there are many technical issues we need to address by using the acidic wastewater treatment process. For example, the acidic process can kind of cause some corrosion of the tank. So that could be a technical issue. We need some support from the civil people as well.
Okay. So we have a comments from one of the audience, Mr. Saying that one of the major challenge of animals is the low temperature, as the bacteria become inactive when the temperature is lower than 25 degrees Celsius. So have Dr. Liu looked at the temperature event?
Yeah, in some of my study, we do investigate the low temperature. For example, 10 degree, around 10 degree. And I think the lowest temperature we tested is 10 degree. It can work perfectly. It's not, there is no problem.
Okay. Oh, so we have a follow-up questions about the FNA levels. Is a high FNA level better or lower FNA level is better?
Depends on the aim, depends on your aim. If you want to achieve suppression of NOB, I have to say suitable level is better. We have an optimal level. The higher level is not good. The lower is also not good. Actually, I saw one of the comments as well from the about the greenhouse gas emission in Hong Kong. So this is I think I want to add one comment. I know the current state because in the case in Hong Kong is currently we have no idea, we have no clue about the greenhouse gas emission in Hong Kong. So that's why we generally believe the power consumption contribute to the most of the greenhouse gas emissions, that's scope 2 emissions. But the fact is for the scope 1, no one measure it yet. So that's why we don't have the data to say whether the scope 1, the direct emission from the wastewater treatment contribute or not. So CEPT will not contribute, but directly discharging into the marine system will contribute a lot of greenhouse gas emissions. So that's why we want to measure it by ourselves to get the accurate number. So yeah, I agree with you. So the current understanding is the energy consumption contribute to most of the greenhouse gas emission, but that may not be true, in fact.
Okay, so thanks for Dr. Liu to clarify with Mr. questions. So, wow, here's the last question is quite long. Oh, okay. So okay, the question is about the administrative words of the seminars. So we will skip this one. And the last question is, how can animals, the NAMO and AOB technologies improve the efficiency and sustainability of wastewater treatment process?
Okay, so efficiency. I would say, I would imagine you say like for example the nitrogen removal efficiency. So as I mentioned, these kind of new technologies can remove the nitrogen pollutants completely from the wastewater. So that definitely can improve the efficiency. In terms of the sustainability, nowadays sustainability is more about the carbon emissions, energy consumption, this kind of concept. So definitely these new technologies, well, we're trying to utilize these new technologies to mitigate the greenhouse gas emission or carbon emissions in wastewater treatment. So that's why we believe they are more sustainable comparing to the current traditional nitrification or denitrification process.
Okay. Thank you, Dr. Liu. So, the remaining questions is about whether we can share the slide with our audience. So, our administrative process will answer you to the questions later together. So, I think there's no more question regarding the seminar. So, thank you, Dr. Liu. And this is the end of today's seminars. So, we will see you in our next seminar. Thank you.
Thank you, everyone. Thank you, Leo.
Thank you.